I am significantly older than most of you, at least twice as old. So you are now accustomed, thanks to the Hollywood movies, to have seen lots of scenes of rocket launches. And you know, in Hollywood movies everything goes fine, and there is a sort of excited atmosphere in the launch. People are nervous but have a happy face. Well, that's true only for those people who are actually in the room making the launch possible. But the real people who are actually suffering are the people in the backwards. These are the people who have spent 10, maybe 20 years of their life preparing a space mission. And they have done it spending an enormous amount of time in very unglamorous places like airports, meeting rooms, hotels, far from their families. And I can tell you, in the last moments before a launch, all your life come in front of your eyes. And you start thinking, have I really screwed actually this cable in the proper way? What if I actually would have done the test of shaking that it was recommended to me by the European Space Agency and I didn't do? Did I always use in a consistent way the units to describe my instruments? Well, at that point it's too late, and you have just to hope that everything goes fine. And for XMM-Newton, almost 20 years ago, everything went fine, and XMM-Newton was born. XMM-Newton actually spent a significant part of his latest life here close by, in the test facilities at ESTEC, here in Noordwijk. And you see, even after 2 years in the Netherlands, I cannot pronounce Noordwijk correctly. That's the real rocket science. By the time when XMM was launched, XMM was the biggest spacecraft, the largest spacecraft ever built by the European Space Agency for research, for astronomy. It was a beast of 10 meter long, 16 meter wide. It weighed almost 4 tons. It weighs 4 tons, fortunately. It carries 6 scientific instruments. It took a consortium of 50 companies, almost 50 companies in Europe and the US to build it, with an enormous amount of scientists and engineers being involved in building it over 20 years. The first document when XMM was mentioned without having, really 80% of you were not born. And XMM-Newton, funnily enough, was designed to last 2 years, and it's still in operation doing science. Anecdotically, since I am much older than the largest majority of you, I still remember a time in Western civilization when politically correctness was not fashionable. And XMM-Newton was known as the black horse, referring to certain anatomical characteristics of this animal. That's no joke. Or it was a joke 20 years ago. Now, I didn't know how actually the talk could be organized, so I have also a quiz. So I need actually the help of a lovely assistant. Ciro, could you please come? Ciro Pinto, he's a much better scientist than I am. He should be giving the talk, not me. Apart from the fact that he's significantly younger than I am. And I have the honor of working with him at ISAC. So, can you actually do something obvious whenever the time comes? So far, no, don't do anything. So, what's that? Who said it? No, that's not valid. No. My wife answering is shameless. Come on. Shut up. Who said? Okay. Congratulations. So, you win the first goodies of the evening. Please give the goodies to the an applause for the man here. So this is the sun. This is, of course, the sun not in the light we are accustomed to use, identify with our eyes the objects surrounding us. This is an image of the sun in X-rays. Not taken by XMM, because if we observe the sun with XMM, all the instruments get destroyed immediately. Now, there are two things that you should take home from this picture. The first thing, it was always stressed by Aurora. We look at the X-ray sky because celestial objects in the X-ray sky are completely different, look completely different, because they are completely different from what we are accustomed to see. The sun is a nice disk, a yellow disk, reddish occasionally in the evening where there are no cloud, too many clouds. And here in this X-ray picture is primarily black, with some small dark spots. And the second thing you should take home from this picture is that these images are different from each other, and they represent 11 years of the history of the sun, a solar cycle. This is typical of the X-ray sky. In the X-ray sky, what you see today is different from what you see tomorrow. And this has nothing to do with the amount of beer you have drunk from one observation to the next. It's because truly the X-ray sky changes, and occasionally changes on time scales of seconds. What you see now and what you will see in 10 seconds will be completely different. Why is that? Well, Aurora mentioned it, and you have just made a game, so you know this, that X-rays are just one of the many forms of electromagnetic waves, like the visible light we see, like the radio, like the infrared, like the gamma rays. Now, your body, or the cake of the question made before, emits temperature, temperature of 20 the cake, 37, you will have a temperature of 20, much more in the future, much more. I hope as far in the future as possible. But now your temperature is 37 degrees more or less, unless you have some fever, which is probably my case now. With 37 degrees, you emit primarily infrared radiation. If you wanted to start emitting X-rays to have a glamorous life in the electromagnetic spectrum, you need to have a temperature of 1,000,000 degrees. Now, I recommend, if you want to make the experiment, I recommend you to make the experiment not here at home. It's actually the experiment of your life, but please don't do it here. So remember, X-rays means hot temperatures, or better said, lots of energy. So high velocity, very strong magnetic fields produce naturally X-rays. And that's why the sky in X-rays is very much different from the sky we are accustomed to see with a telescope in the optical. So that's another question. What's that? You have already answered, so you're... nice try. We'll have a chat later. So, what's that? Oh, shut up. The Earth? No, it's not the Earth. Nice try, however. Bit farther away. The moon. Moon? No, it's not the moon. Bit farther away. Mars? Slightly farther away. Yes, you one, please. Goodies for the lady. Both the mouse pad and the keyring. An applause for the lady. So, this is Jupiter in X-rays, observed by XMM-Newton. So, of course, it's completely different. I could spend hours to say why, but I just want to stress one specific feature. What's that?
Oh, red spot.
No, stop. Be careful. That's Jupiter image. The red spot is here. The spot here is there. That's the North Pole, correctly. So, what actually is this X-ray spot due to? Brava! So, just the mouse pad, because that was an easy question. That's exactly the auroras. So, through XMM, we have discovered that planets, they have auroras exactly as we observe on the Earth. And the mechanism is the same. Electrons at high velocity in a strong magnetic field of the planet. Now, this is another example of how the sky looks like in X-rays. This is a galaxy, Aurora, not the one on Jupiter, the one here. She mentioned this, it's M31, is the biggest object you can see with naked eyes on the sky. And you see in the optical, in the infrared, and you see the strange image in X-rays in this corner. And you know, everywhere you see lots of diffuse emission, but in the X-rays, you see just single spots. What are they? That was not a question for a prize, but you may deserve a prize. Anyway, these are systems where we have a star, in very general terms, a star loses matter and create accretion disk, so a disk of matter which is slowly spiraling and falling on a hole. And the hole could be a real black hole or a strange object like a neutron star. For the sake of what I'm going to show you now, it doesn't matter what it is. What is important is that there is a big mass creating a strong gravitational pull that forces matter to fall, to be eaten from the star and fall onto it. And when this process happens, this gas, which is spiraling towards this big mass at the center, acquire quickly very high velocities, velocities that are close to the speed of light. And if there is an efficient way to convert velocity into radiation, this radiation will have the million degrees condition to be observable in X-rays. And that's what actually these systems primarily are systems where matter falls on a black hole or a neutron star, is heated so much that it emits X-rays. Now, these X-rays, remember I showed you the variable sun, these X-rays change their intensity, change their energy very, very quickly. This is an image I take from one of the several thousand of scientific papers have been published on XMM so far. The axis, on the x-axis, there is something that is basically time. And you see that actually the emission with time of this object, of this accreting black hole, is breathing. Higher energy, lower energy. Higher energy, lower energy. Now you know this, because you're interested in astronomy. This is the first image of a black hole. Very beautiful image. Something that it is not told to you, the fake news behind this image, is that in X-ray astronomy, we make images of black holes since decades. Because actually, what this breathing of the X-ray radiation is telling you is that the accretion disk close to the black hole is not staying always on the same plane. It's doing this way. It's precessing, as we say in astronomical terms. And this precession is a prediction of the general relativity. As important as the prediction of the general relativity that is behind the first image of the black hole. And this is something that can be done, this kind of measurements of the breathing can be done only in X-rays, because this kind of objects emits basically only in X-rays. Now, black holes are everywhere in the universe. They are behind the corner. They are at the center of our galaxy. And this video, which I would like to repeat, but I can't, showed you a series of stars at the center. Thank you. These are a series of stars at the center of our galaxies. And at the end, you see actually the orbits that these stars create. And you can see that actually these stars, they orbit around the point where there is nothing, where you see nothing with the poor optical eyes. This is not an image in X-rays. This is an image in infrared of the center of our galaxy. All the stars at the center of our galaxy, they rotate around an invisible point in the sky, making perfect ellipses. Now another celestial system where objects rotate in ellipses around the point. The solar system. And what did the solar system allow Kepler to do in the 17th century? You seem to be a smart guy. Tell everybody. What was the solar system used by Kepler in the 17th century?
For the planets orbit around the sun.
Yes. And if you know the orbits of the planet, you can know which is the mass of the sun. In the same way, we know which is the mass of this invisible point that we actually observe, that we see, around which the stars rotate at the center of the galaxies. And this mass is 4 million times the mass of the sun. What does this have to do with X-rays? Why I'm wasting your time with a boring infrared image? Because when you look at the center of our galaxy in X-rays, not only we see evidence of the black hole at the center, because there is some occasional flaring of the gas with very high temperatures that we can measure in X-rays, but we also see enormous diffuse gas, which on the scale of several thousand the scale of the solar system, which is actually this orange image. This is an image from a paper published in Nature 3 months ago, just to show you that we don't keep satellites in orbit just because we like iron stuff to be over there. We still produce science. And why is actually this diffuse emission so interesting? Because if you have this hot gas on such a large scale, close to the center, something must have energized this gas, must have given to this gas sufficient energy to radiate in X-rays. And this one was the black hole at the center. But not the miserable black hole that we see nowadays at the center of the galaxy, which is almost switched off. A black hole whose intensity in X-rays was millions of times larger than nowadays, just a few centuries ago. Basically, at the time when the Netherlands, gained its independence from Spain. At that time, the black hole at the center of our galaxy was 1 million of times brighter than nowadays. The next question you should ask, because I've been asked this question every time, is, was it dangerous? No, Spaniards were much more dangerous. However, only because we are sufficiently far away from the center. Because all planets that were located 3 kiloparsec from the center of the galaxy, probably every intelligent form of life would have been killed by the burst of the black hole. And we are fortunately around 10 kiloparsec away. So you may imagine that in this moment, in the innermost 3 kiloparsec of our galaxy, there is no intelligent form of life, only clones of Donald Trump. Don't go there. Now, black holes are everywhere. Black holes are at the center of almost each galaxy, we believe. And some of them are very active. Some of them are not like the miserable, weak black hole at the center of our galaxy. They emit lots of X-rays. They have the powerful X-ray relativistic jets Aurora was talking about. The Aurora here, not that on Jupiter. And how do we know that? There are two ways you can identify a celestial body in the sky. Either because it emits light or because it takes away light from a very strong lamp behind it. And when we observe the center of an active black hole with X-rays, with XMM, we see both things. We see both the radiation that is emitted from close to the black hole, the gas at speed close to the speed of light and with a temperature of 1,000,000 degrees, but we also see gas that is between the galaxy and us, and that actually remove radiation. And we see actually this when we plot the distribution of light as a function of energy. We see sometimes holes, which are regions, energies, where radiation is eaten by matter close to the black hole. And what is that? These are exactly the signature of these powerful outflows, this powerful wind that black holes ejects. And actually that has been one of the fundamental discovery of XMM-Newton. Why is it interesting to discover that black holes emit winds and jets? You know, we all human beings, we emit lots of things, and most of them are unpleasant, so why should we bother? Because this measurement allows us probably to solve one of the big mysteries in modern astrophysics. I told you most of the galaxy, they host a black hole at the center, big one, millions, billion times the mass of the sun. And we know that the larger the galaxy, the larger the black hole, but we don't know why. And you may say, well, it's obvious, the larger the black hole, you know, there is a sort of correlation between the two things. They fill each other. No. The black hole is as big as a euro coin, and the galaxies is as big as the Earth. And as much mass as you can put in this euro coin, even if you put 1 billion solar masses, you can't actually make that there is a direct influence of the black hole on the galaxy. And our hypothesis that XMM-Newton has put forward is that it's actually this wind that carries sufficient energy from the black hole to the host galaxy to create this mysterious correlation. Now, Aurora told you about the fact that the universe is not homogeneous nowadays. That's an obvious thing. You know, we are separate human beings. We live in a solar system with separate planets. We live in a galaxy which is separate by other galaxies. All this is evidence the universe is now highly inhomogeneous, but it used to be very homogeneous in the past. At some point, structure formed in the way Aurora showed with her computer simulation. And believe it or not, why do we want to study them in X-rays? Why do we want to study this inhomogeneity in X-rays? Because the gas in this inhomogeneity is very hot. This gas has 1,000,000 degrees temperature. And that's why we are so interested to study the object Aurora was talking about, or this inhomogeneity of the sky in X-rays. However, there is a problem. You all know that astronomers are cheating you every single day. They tell you that they know about the universe, and they know nothing about the universe. Let's face the reality. Of the universe, we know only the 5% of matter that emits lights, because these objects justify the money that we spend in expensive observatories. But we have no idea what the remaining 95% of the components constituent of a universe is. And since I don't know either, I also ignore them. And I concentrate on the 5% that justifies the fact that we have spent millions to build XMM-Newton. But even more seriously, out of this tiny, miserable 5%, 40% of it, we have no idea what it is. And the suspicion is, maybe, it's an hypothesis, No, I'm laughing myself inside. The suspicious is that you can see it, you can look at it, by looking in X-rays at regions where you see these filaments, this inhomogeneity, which, I remind you, are on a scale which is much, much larger, not only of each single galaxy, but even of the cluster of Galaxy Aurora was talking about. It's 1 million times larger scale than our galaxy. So we point XMM-Newton, and let's see what happens. First of all, we see that we distribute the light as a function of energy. Ignore, this is energy for all practical purpose. And there are some regions where they are missing light. And I remember I told you there are two ways of identifying a source in the sky. Either because it gives light to us, or because it takes light away from us. And this is exactly the case. We are pointing at a region through actually this filament where we suppose that there are this filament of hot gas. And we discover missing light. And this missing light is exactly the amount that we expect if along this direction there is gas, hot gas, associated with large scale structures. So we have for the first time a clue to know what this 40% of the miserable 5% of matter we know. We have at least a clue to know what it is. And that's also very recent results published on the prestigious Nature journal last year by XMM-Newton. Now, when I was asked to give this talk, the organizer asked me also to give a personal touch. So, since I don't think I've given sufficient personal touch to this talk so far, I would like also to, tell a sort of a personal story. And the personal story is that XMM-Newton has been my own professional life for 15 years. I used to work in the so-called science operation of XMM. So my work was going to work every day, praying that the satellite was still there and working, otherwise I would have been fired, and then helping other scientists like Aurora to do their own science. I don't know if I made a good job out of it. I'm not doing it any longer now. Give the interpretation that you want to this fact. But these 15 years for me in Madrid has been a tremendous experience, not only from the professional point of view, but also from the personal point of view, because this gave me the opportunity of living what I think is a truly unique period of the history of this country and probably from Europe, enjoy immensely my life in Madrid, not the least because it's still the only country in Europe I'm aware of where a beer costed only €1. Unless it's offered by the organizers. Thank you. So you may ask, if you were so happy in Spain, why did you come to this country? Come on, you only complain about, why didn't you come to this country? And it's a fair question. I came here for love. It's not what you think. It's for love for the future of X-ray astronomy. Well, that's unfortunately true. So XMM is a wonderful machine, but as I told you, it takes of the order of 20 years from the time you start thinking about a mission to the time when you can actually start thinking if you actually tied all the screws correctly. So already now, and since a couple of years, we are preparing the next mission, the next X-ray observatory, that will be 100 times more powerful than XMM in collecting photons, will be 10 times more powerful in detecting these small blips, this small lack of energy that we see when we spread the photons as a function of energy, will be able to measure black holes at a distance 5 times farther away than we're able to do with XMM now, will be able, in a nutshell, to do a completely new science. This is called Athena. It will be launched in 2031, hopefully. And there is always a team of more than 800 scientists several hundred engineers, and actually companies in Europe, groups in Japan and the United States who are already working 24 hours per day minus some time for beer to prepare it. And this is just to tell you that if XMM-Newton is still working and still getting wonderful science, there is already actually room and need to prepare the future of X-ray astronomy to get even more discoveries. And say that, I'm very glad I thank for your attention, and I'm very glad to answer any questions you may ask. But be careful, normally when you ask a question, I normally ask a question to you. Okay, thank you.